Hello, and welcome back to Atomic Math. Today we're going to talk about the ideal gas law. And in order to understand the ideal gas law, it's important to understand what all these little gas molecules are doing. So the first thing that we're going to talk about is the laws that make up the ideal gas law. The first one is Boyle's law. And Boyle's law states that if the number of molecules and the temperature remains constant, the volume is inversely proportional to pressure. So let's imagine our little container here that's filled with little gas molecules. Let's say that I reduce the size of this box, but the number of molecules is the same and the temperature is the same. So what's going to happen is that when these little molecules hit the side of the container, that's what's creating the pressure. So if I've now confined them to a smaller space, they're going to start hitting the wall more often, which is going to cause an increase in pressure. And this is why volume is inversely proportional to pressure. The volume goes down, the pressure goes up, as long as we're holding temperature and number of moles of gas constant. The second one is Charles' law, and this states that if the number of molecules and the pressure remain the constant, the volume is proportional to the temperature. So let's now make our box big again. In this case, I'm saying that the pressure can't change and the number of moles can't change. So basically, now I have these little molecules, they're now moving around in a bigger space, but they still have to hit the walls as often as they were before. Now, if you have to cover a bigger distance in the same amount of time, there's only one way to do that. You need to move faster. And for gas molecules, that means they have to increase the temperature. So the higher temperature helps the molecules move faster, and they're able to continue to hit the sides of the container at the same frequency that they were when the volume was smaller. The third one is Avogadro's law, and this states that if the temperature and the pressure remain constant, the volume is proportional to the number of molecules. So again, let's change this. Let's make this small again. Now, I have the same temperature, so I can't change the speed of the molecules. I have the same pressure, so I can't let them hit the sides of the container more often. The only way that I can reduce the volume and keep those two facts true is if I reduce the number of molecules that are in there and make room for the other ones. So that is why we would say that volume is proportional to the number of moles. So now we have three equations. We have volume is inversely proportional to pressure. We have volume is proportional to temperature, and volume is proportional to the number of moles. So we can combine this because they are all proportional to V and say that V is proportional to the number of moles times temperature divided by pressure. Now notice I'm not saying equals here, I'm saying proportion to. And that's because what we're really saying is that the rate of change is the same. So if I double temperature, I double volume. If I double the number of moles, I double the volume. If I double the pressure, I half the volume. So the only difference really between equals and proportion is some constant value. And so we add a constant R, and we end up with this. If we rearrange this a little bit, we get what we typically think of as the ideal gas law. And R is called the ideal gas constant, and its value is 0.08314 liters bar moles per Kelvin. Okay, so we'll save that for later. Because we live in an environment that is approximately 1 bar, unless our gas that we're talking about is confined in a rigid airtight container, the pressure is usually held constant, as is the number of molecules. So when we're working with questions sort of exposed to the natural environment, we can basically say that the ratio of the volume to the temperature is equal to the number of moles, the constant, over the pressure. And of course, this whole side is going to remain constant. So I can also say that V initial over T initial is equal to this constant, and therefore V final and V and T final must be also equivalent. So I can just get rid of this middle term and directly say that my ratio of my initial volume temperature has to equal my ratio of final volume and temperature. Okay, suppose we have a balloon filled with helium at a temperature of 293 Kelvin inside a store. You leave the store and you notice when you reach your car that the balloon has reduced its volume by 15%. What is the temperature outside? Well, let's rearrange this equation because we know that we want to solve for the final temperature. Now, the final volume is unknown, but we do know that it is 85% of the initial volume. So we can replace the V final with 0.85 V initial. And then we have this. And of course, the VI's can just cancel. And what I'm left with is the final temperature is equal to 0.85 times the initial temperature, which was 293. And this is going to give me 249 Kelvin, which is about minus 24 degrees Celsius, aka a normal winter day in Canada. Now, one of the things that's important is to know, why do we call it ideal? There are two things that we are kind of ignoring when we use this. But the thing is that at regular temperatures and pressures, these things are pretty negligible. The problem arises when you get to really high pressures or really low temperatures. Let's look at what they are. The finite volume of the gas particles themselves. So if I make our box bigger here, we can see, of course, this is an exaggeration and gas molecules are not this big, but you can still imagine that some of the volume inside this container, let's say it's a 1 liter container, there is not 1 liter of free space. A small amount of that volume is actually taken up by the molecules themselves. So that is one of the things that we are kind of ignoring. The other thing is intermolecular forces. And this is the attractions that happen between molecules. And a common one would be the hydrogen bond. So let's just take a closer look at our ideal gas equation. If I rearrange this for volume, I have this. Now, if I want to correct for that volume, I need to add a little extra piece to account for that volume that the molecules are taking up. And so our equation becomes something like this, where N is the number of moles and B is a constant. And of course, if I move this over to the other side, then I can say that instead of just volume, I'm going to have V minus this little factor to give me my true volume. And that's going to correct for the volume. Now, when it comes to the intermolecular forces, it's a little bit more complicated. In order to correct for that, we have this term added here, where A is a constant, N is the number of moles, but we have to include the volume in this. The volume is going to play a part. And if we move this to the other side, the way we did the first time, we're going to end up with, instead of just pressure, we'll have this term representing pressure, but it's the corrected pressure. Now, if we put these together, we get what's called the van der Waals equation. And if you look at it here, basically what we're doing is saying that this is the P and this part is the V equals nRT. So it may look a lot more confusing, but it's really just using these two extra values, A and B. And they are constants that are specific for each type of gas. Usually you would have a table and you would look up the values for whatever gas is in your particular container. The next thing that I want to look is partial pressures. We have Dalton's law of partial pressures. So let's take a closer look at our box. In this container, you can see 3 different colors of molecules. So let's call them A, B, and C. So 3 different gases, A, B, and C. So we'll put our container back. And Dalton's law says that the total pressure in the container is the sum of the pressure of the A molecules, the B molecules, and the C molecules. Now, we know that our ideal gas law says this. And if we rearrange this to solve for pressure, we know that we can say that it is equal to the number of moles times the constant times the temperature over the volume. But in this container, all the molecules are experiencing the same volume, all the molecules are experiencing the same temperature, and of course the constant stays constant. So the only thing that's really changing when I move from one pressure to the other is just the number of moles. So we can write this like this, and as I said, these pieces are all constant, so we can actually just pull them out. And we end up with this. So our total pressure is equal to the sum of the number of moles of gas times our constant values. Now, the sum of the moles of the 3 gases is just the total number of moles in the container. So we can also just say that the total pressure is equal to the total moles times the constant times temperature divided by volume. So if I wanted to know the ratio of the pressure of gas B, let's say, I could write it like this. pressure B over pressure T is equal to the number of moles of B times our constant values divided by the total number of moles in the container times our constant values. And of course, these things are just going to cancel out. And we're going to be left with the ratio of the pressure for gas B is equal to the ratio of the number of moles for gas B. And this is usually given the symbol X, and it is called the mole fraction. So I hope this information helped explain the ideal gas law, helped you understand molecule-wise why these facts are true, and hopefully you're a lot more comfortable now with this equation. So if you like this video, go ahead and hit like, and if you want to see more videos like this, hit subscribe, and I will see you in the next video.